Hello my dear students, welcome to the second class of the unit solution. In today's class we are going to discuss non-ideal solutions, deviation from Raoults law, vapor pressure composition and temperature composition curves, distillation, Azeotropes and the lever rule. If you haven't watched the first lecture on this unit, please see the link for the lecture 1 in the description box. So let's start our today's class with the non-ideal solution. The non-ideal solutions are those which does not follow the Raoults law. In fact, all the solutions are generally non-ideal except a few at certain compositions. There are two types of non-ideal solutions. Type 1, which shows positive deviation from Raoults law, and type 2, which shows negative deviation from the Raoults law. The characteristics of the type 1 solutions are: these solutions do not obey the Raoults law. The enthalpy of mixing as well as the volume of mixings are always positive, and the solute-solute interactions are weaker than the solute-solute and solvent-solvent interactions. As a result of this, the non-ideal solutions exhibit higher vapor pressure than that predicted by the Raoults law. In our first class, we have seen how to construct the plot of vapor pressure against the mole fraction for an ideal solution, which is shown by the dotted lines in this figure. The solid lines represent the variation of vapor pressure against mole fraction for the non-ideal solutions which show positive deviation from the Raoults law. Examples of some non-ideal solutions showing positive deviation are mixture of ethanol and chloroform and mixture of acetaldehyde and carbon disulfide. So these two solutions are non-ideal solutions showing positive deviation. Let us consider the example of mixture of ethanol and chloroform. In this mixture, there will be no interaction between the molecules of ethanol and chloroform. That means the interaction between the solute and solvent is weaker. As a result, more number of molecules will escape into the vapor phase, and more number of molecules will exhibit higher vapor pressure. Therefore, the vapor pressure of such solution is higher than that predicted by the Raoults law. Similarly, in case of the type 2 non-ideal solutions, the characteristics are such solutions also do not obey the Raoults law. The enthalpy of mixing as well as the volume of mixing are less than 0 or negative. In this case, the solute-solute interactions are stronger than the solute-solute and solvent-solvent interactions. As a result, the non-ideal solutions exhibit lower vapor pressure than that predicted by the Raoults law. So similarly, here also in this figure, the variation of the vapor pressure against the mole fraction for non-ideal solutions showing negative deviation is shown by the solid lines. So few examples of such solutions are acetone, mixture of acetone and chloroform, and mixture of water and nitric acid. Okay, if we consider the example of acetone and chloroform, then we'll see that there will be a hydrogen bond formed between the molecules of acetone and chloroform. As a result of this, the interaction between the molecules of acetone and chloroform are stronger. Hence, a lesser number of molecules will escape into the vapor phase, and consequently lesser number of molecules exhibit lower vapor pressure. Is it clear? Now let us see how the vapor pressure of non-ideal solution changes with the composition. To discuss this, consider a binary mixture prepared by mixing two volatile components A and B. Now when the mixture is heated, the molecules of both the components starts evaporating. The vapors of the liquid components exert vapor pressure. At the same time, the atmospheric pressure also act upon the vapors. So the temperature at which the vapor pressure equals to the atmospheric pressure is known as the boiling point of the mixture. Lower the vapor pressure exhibited by the components, higher is the boiling point, because if the vapor pressure is low, then high temperature is required so that the vapor pressure equalizes with the atmospheric pressure. On the basis of this, we can construct the vapor pressure composition and the temperature composition curves. So there are three types of such curves known as type 1, type 2 and type 3. To discuss such type of curves, we have to consider that the liquid phase and the vapor phase both are in equilibrium with one another. Let us discuss the type 1 mixture. In type 1 mixture, the vapor pressure changes continuously with the composition of the mixture as shown in figure A. So in this figure, the vapor pressure of pure A is the lowest and that of pure B is the highest. But as shown in figure B, the boiling point of pure A is highest and the boiling point of pure B is the lowest, because already we have seen that if the vapor pressure is low, then the boiling point is high and vice versa. So since the vapor pressure of the mixture lies in between the two extreme values, so the boiling point also lies in between. So this figure A is the vapor pressure composition curve and this one is the temperature composition curve. Okay. In case of type 2 mixtures, the vapor phase shows a maximum in its vapor pressure composition curve, say at the point C as shown in the figure C. This is the vapor pressure composition curve of type 2 mixtures. Now as shown in the figure D, the solution at that composition will boil at the lowest temperature, because the vapor pressure becomes maximum, means the boiling point becomes minimum. So this gives a minimum in the boiling point curve as shown in the figure D, which is the temperature composition curve for the type 2 mixtures. On the other hand, in case of type 3 mixtures, the vapor pressure curve shows a minimum for a certain composition, say at point D as shown in the figure E. So this is the vapor pressure composition curve for type 3 mixtures. Now as shown in figure F, the solution of that composition will boil at the highest temperature, and as a result the boiling point curves show a maximum at the point D. This is because since the vapor pressure is lowest, so the boiling point is the highest. Okay, so the figure F is the temperature composition curve of the type 3 mixers. Now let us move on to the next topic, distillation of liquids. Distillation is a purification method for liquids and can separate the components of a mixture if they have significantly different boiling points. In a distillation process, a liquid mixture is boiled in the distillating flask as shown in the figure. Then the vapors travel to another section of the apparatus, which is known as the condenser, where they come into contact with a cool surface. The vapors condense on this cool surface and the condensed liquid known as the distillate drips into the reservoir separated from the original liquids. Now let us consider that we have a mixture of two liquids A and B, and A has lower boiling point than that of B. If we heat this mixture up to the boiling point of A, then the molecules of A will undergo distillation and the vapors of the molecules of A will pass through the condenser, on which the vapors of molecules of liquid A undergo condensation, and then the condensed liquid drifts into the reservoir, and this way we can separate the liquid components A and B from the mixture. On the other hand, if the difference in boiling point of the two liquids are less than 20 Kelvin, then another process is used, which is known as fractional distillation. In this process, a fractionating column is fixed with the distillation apparatus, through which the molecules of both the liquids A and B undergo evaporation, and in the fractionating column the molecules of the liquid which have a higher boiling point will again bounce back into the distillation flask. Therefore, only the liquid molecules whose boiling point is lower will undergo distillation through the condenser, from where it is again converted to the liquid phase. So in this way we can separate the components of the mixture by fractional distillation process. We can also understand the concept of distillation or fractional distillation from the temperature composition curve. So let us consider a type 1 binary solution. The temperature composition curve is shown in this figure. In the figure, suppose a solution of composition X is heated. The solution boils at temperature T, this point. At this temperature, the vapors coming off will have composition X1, this point. Since X1 is richer in B, because in this side the mole fraction of B is higher, so therefore the composition of the residual liquid will be richer in A. Let it be point Y. This liquid, now having a different composition, will boil at temperature T1. The vapors coming off again now will be richer in B, as represented by the point X2, this one. Consequently, the composition of the residual liquid will be further enriched with A. So if this process continues, ultimately only liquid A remains in the liquid phase. So therefore we can separate the liquid A from the mixer. So this concept can be also understood with the help of this temperature composition curve. With the help of such temperature composition curve, we can determine the composition of the liquid and the vapor phase using a simple rule known as the lever rule. To understand this, let us consider a two-component temperature composition diagram of the components A and B. Clearly, from this figure, the boiling point of B is that is TB naught is less than TA naught. In this system, the composition of the liquid and the vapor phase can be determined with the help of the lever rule. According to this rule, if we draw a horizontal line through any point A and let it meet the liquid in equilibrium with liquid plus vapor curve at L and V, then the ratio of the amount of liquid phase to the vapor phase is given by N liquid divided by N vapor equal to length of AV divided by length of AL. This is the lever rule. Now the next topic is the constant boiling mixture or Azeotropes. Let us consider a temperature composition curve of type 2. In this curve, C is a minima point at which the liquid and the vapor phase have the same composition. Thus, the liquid mixture represented by the point C will boil at constant temperature and will distill over completely without change of the composition. Such a mixture, which is like a pure liquid, boils at a constant temperature and distill over completely at the same temperature without the change of its composition, is called an azeotropes or constant boiling mixture. There are two types of azeotropes: the minimum boiling azeotrope and the maximum boiling azeotrope. The azeotrope which has the boiling point lower than the boiling point of either of the two components is called the minimum boiling azeotrope. For example, 95.5% by mass of ethanol and water mixture is an example of minimum boiling azeotrope. Okay. On the other hand, the azeotrope which has the boiling point higher than the boiling point of either of the two components is called the maximum boiling azeotrope. For example, 68% by mass of nitric acid and water mixture is an example of maximum boiling azeotrope. Okay. So this is all about today. If you have any doubts, then you can post your comments in the comment box. I will be waiting for your comments and I hope for a fruitful discussion here. So see you in next week. Till then, enjoy learning.